Hello friends, welcome to BSc third year mathematics class. In this semester 6, we will study real analysis second part, which is paper number MAT 601, real analysis second. In this paper, we are going to study metric spaces and then functions on metric spaces, open set, closed sets. Then the properties of metric spaces we will study as connectedness, completeness, compactness, and the further part we are going to study is calculus. So this is the content of this paper, and the recommended book is the same, which is Methods of Real Analysis by Richard R. Goldberg. So we will consider the first chapter today, that is limits and metrics. Limits and metric spaces is the first chapter. And see, limits usually we have studied earlier. Limit of a function, limit of a sequence, that we have studied. What is the new concept we are going to study is metric. And a metric system is means roughly a measurement system. Metric is a measurement or which measures, and roughly we are considering distance. Metric is a distance function defined differently for different sets. Now we will first consider again the absolute value properties of absolute value function. So some properties of absolute value function we will revise. Absolute value function we have defined earlier. If x is real number, then absolute value function denoted by this symbol is equal to having two values, x when x is greater than or equal to 0, negative x when x is less than 0. That is the definition of absolute value function. And these properties are according to the definition. Simple. When x is 0, it is x. Absolute value of x is x. So absolute value of 0 is 0. Further property can be considered as absolute value of a is greater than 0 if a is not equal to 0. So absolute value results always positive number, real number, and therefore absolute value of a is greater than 0 means it is non-negative. Absolute value of negative a is same as absolute value of a by definition. It is resulting positive. So we know mod of absolute value of minus 3 is same as absolute value of 3. And again, absolute value of a minus b is same as absolute value of b minus a. Further, absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So these are some properties of absolute value function that we have studied earlier. Now what we shall consider is two real numbers. For x and y, two real numbers. We define a function rho of x and y is equal to absolute value of x minus y. And what this means geometrically is the distance between x and y. Because if you consider absolute value of 5 minus 3, then it is 2. And this means distance between 5 and 3 is 2. Or that is same as distance between 3 and 5. So by this property. So this means the distance between x and y, geometrical meaning is absolute value of x minus y means the distance between x and y. And now this function satisfies the following properties. So geometrically it means absolute value of x minus y means distance between x and y. So we have the following properties further, as according to these properties of absolute value function. We have, see, first property can be considered as rho of x and x. Rho of x and x, which will be absolute value of x minus x, absolute value of 0, and that is 0. Rho of x and y, that will be strictly greater than 0 when x is not equal to y. X, y are real numbers, and again further rho of x and y is same as rho of y and x. So what is the geometrical meaning of this? Distance between x and x is 0. Distance between x and y is non-negative or positive when x and y are distinct points, and this means distance between x and y is same as distance between y and x. And one more property will be distance between x and y is less than or equal to distance, or that means rho of x and z plus rho of z and y. That is, the direct distance between x and y is always less than or equal to the distance between x and z plus the distance between z and y. So this is known as triangle inequality. The last property is known as triangle inequality. Because if we have these points x, this as z and this as y, and if you join these points, we may observe the distance between x and y is less than or equal to the distance y as z, x to z and then z to y. So that's why this way distance is greater than or equal to the distance between x and y. This is the shortest distance. Direct distance is the shortest distance. So these are some properties which are defined through this distance function, absolute value of x minus y. And with the help of these properties, now we will define a metric, and we will now consider the definition of metric. Let M be a set and rho be a function defined from M cross M to the range is 0 to infinity. Be a function which satisfies the following property. First is rho of x and x is 0. Second, rho of x and y is greater than 0. Here x belongs to M. Here x, y both belong to M, and x not equal to y. Third is rho of x and y is equal to rho of y and x. X, y belongs to M. And the fourth is rho of x and y is less than or equal to rho of x and z plus rho of z and y. Here this is known as triangle inequality. X, y, z belongs to M. And the last property is known as triangle inequality. Then, see, if this is the function defined from this Cartesian product of M with itself to non-negative real numbers having these properties, and which are the same properties we have seen. This is satisfied by the absolute value function x minus y. And then rho is called a metric. Rho is called a metric on the set M, and the order pair M and rho is called the metric space. So this is called a metric. Rho is metric and the pair is called metric space. So this is the definition of a metric and metric space. So matrix simply is a function and having satisfying these properties. Rho of x and x, or that is distance between x and x, is 0. Distance between two distinct points is positive, and distance between x and y is same as distance between y and x. Distance in the sense of metric we are saying. So metric means distance function, and this is triangle inequality. Direct distance between x and y is always less than or equal to the distance between x and z plus the distance between z and y, and that is the triangle inequality. If these four properties are satisfied by the function rho, it is called metric. Metric on the set M. And then the order pair M, the set together with this metric defined on the set, is called the metric space. So hereafter we shall denote the metric space M rho simply by M. We denote this metric space M rho simply by M. Rho is always assumed there. Metric must be there always, and it is denoted by M. Now we will consider some examples of metric space. Examples of metric spaces. First example we will consider the same as earlier we have seen. Let R be the set of real numbers. This is usual notation. We define a row on R by rho of x and y is equal to absolute value of x minus y, absolute difference between x and y. And then this row is a metric on R, real numbers. Then rho is a metric on R. How? It is easy to verify these properties. See, first is rho of x and x, that is absolute value of x minus x, that is 0. rho of x and y absolute value is greater than 0 if x is not equal to y. And the third is rho of x and y is same as rho of y and x. That follows by the properties of absolute value function. That is absolute value of x minus y is same as absolute value of y minus x. And the third triangle inequality, fourth is the triangle inequality. So the properties are easily verified since, we can write it quickly, since first is rho of x is rho of x minus x, that is 0. Next is rho of x and y is rho of mod of or absolute value of x minus y, and this is greater than 0 if x is not equal to y, or this happens for all x y belongs to R. And next is rho of x and y is the absolute value of x minus y, and which is same as absolute value of y minus x, which is same as absolute value of that is rho of y and x. This we will consider for x, y, z belongs to R. Z we will consider now. And the triangle inequality. Now rho of x and y is equal to absolute value of x minus y, or this can be written as absolute value of x minus z plus z minus y. We have subtracted, added z, and this by the property of absolute value function, mod of or absolute value of x minus z plus absolute value of z minus y, or which is same as that is the last is same as rho of x and z. So this is the last one is rho of x and z plus rho of z and y. And that is the left side is the inequality is less than or equal to between rho of x and y. Thus, this function satisfies all the four properties of a metric, and therefore this is a metric on R, and thus the rho of xy this rho of x and y defined by absolute value of x minus y is a metric on R. This metric or this metric space R and rho. Metric space always we denote m and rho. M here is the set of real numbers. M is a set and we are considering here it as R. So this metric space R and rho is denoted by R1, and the metric is called absolute value metric. This metric is called absolute value metric. So this is our first example for metric spaces. The set of real numbers with this metric, which is defined by absolute value of x minus y, is the metric space that is denoted by R1, and this metric is known as absolute value metric. Now we will consider the second example. Let D be a function D from R cross R to 0 to infinity, defined by the definition for D is D of x and x is 0. X belongs to R. And D of x and y is 1. X, y belongs to R. X is not equal to y. See, this is the function defined having two definitions. Distance between x and x, that is a point and itself, is 0. It's obvious. And distance between, this is important, distance between x and y is 1, fixed to be 1, when x is not equal to y. So that will mean here D of, if x and y are real number, so D of say 3 and 7, it is 1, because 3 is not equal to 7. So that is defined like this. Distance between two distinct points is defined to be 1. So by definition. And then this D is a metric that we shall verify. That is distance between any two distinct points is 1, fixed to be 1. Then D is a metric. Metric on R cross R, and that is R2. Now this is also easy to verify. There are 4 properties of metric. The first is by definition. D of x and x is 0. So D of x and x is 0. X belongs to R. So this is by definition. Second, D of x and y. If x and y are different, this is equal to 1, that is greater than 0. If x is not equal to y, x, y belongs to R. That is obvious. Distance between two distinct points is 1, and that is greater than 0. This is the second property of definition of metric. And third is D of x and y is same as D of y and x. So if x and y are equal, then both are 0. Then these are equal. If x and y are different, then this is 1 and this is also 1. So therefore the third is satisfied. And what about the last one is D of triangle inequality. D of x and y is less than or equal to D of, here also x, y belongs to R, D of x and z plus D of z and y. X, y, z belongs to R. Now this is, suppose all are distinct, then the distance will be 1. So 1 is less than or equal to 1 plus 1, that is obvious. And if any two are equal, suppose x is equal to y, then this is 0. And if all the three are say the same, x is equal to y is equal to z, then this will be 0, this will be 0, and this will be 0 till the inequality satisfies. So in any case, this triangle inequality is going to be satisfied, and therefore this is a metric. This satisfies the 4 properties of metric. Therefore D is a metric. D is a metric on R2. This metric is known as discrete metric. is known as the discrete metric and the metric space. Metric space R2D is denoted by RD. So thus we have the second example of metric space. Now we shall consider the third example. We are taking some sets and we are taking some function, distance function, and we are so that the distance function satisfies the four properties of a metric. Then it becomes a metric and the space is the metric space. Having different name, here it is discrete metric. Third example we will consider, let n be a positive integer. N is fixed positive integer, and let x is equal to x1, x2 up to xn. N tuple, see pair of n components x1, x2, xn. Y is y1, y2 and so on yn. Now this will belong to the set Rn. Define row by row of x and y is equal to summation k taking value 1 to n xk minus yk whole square, and this whole is raised to half. So then we shall verify this is a metric on this space of n dimension. This has n components, so therefore this will belong to Rn. So earlier we have considered order pair belongs to R2, triplet belongs to R3, and this is n components belongs to Rn. Then row is a metric. This row defined in this particular example. We are defining row differently for different examples. Then row is a metric. Metric on Rn. So how to verify the properties? First property is row of x and x is 0. That is obvious. Now first three properties are obvious in metric spaces. See what are the properties that we have defined in metric spaces. That is row of x and x is 0. Row of x and y is greater than 0. X not equal to y. Row of x and y is equal to row of y and x. And the triangle inequality, row of x and y is less than or equal to row of x and z plus row of z and y. So these are the four properties of a metric space. Now we will verify these properties for this. So first is row of x and x. Because x and y are equal, these two becomes equal, and that becomes obviously 0. So the first is satisfied. Now what about the second? X and y. X is different from y. So therefore these xk is different from yk. At least one xk is different from one yk. So therefore this is non-zero. And therefore this quantity becomes greater than 0. It is square. And positive root is assumed. So therefore the second property is satisfied. And this can be interchanged in square. We know that xk minus yk square. Square of xk minus yk is same as square of yk minus xk. This can be interchanged in the square, and therefore row of x and y is same as row of y and x. So first three properties are obvious. Now what remains is to prove the triangle inequality. So first three properties. Properties of the matrix are obvious. Obvious or trivial are easy to prove. Consider the triangle inequality. We will verify or prove the triangle inequality. For triangle inequality, we require 3 points. And x and y are taken here. We consider z. Let z be z1, z2, zn be a point considered. Now, row of x and y by definition is this, and I shall write in this curly bracket summation k takes value 1 to n xk minus yk square of this, and then whole is raised to half power. We will write this as summation k takes value 1 to n xk minus zk plus zk minus yk, and I will put this in a bracket. See, both are the same. We have subtracted zk, we have added zk, and we will assume this as this first bracket as ak and the second bracket as bk, this bracket as bk, and again we are see where ak is AK is xk minus zk, bk is zk minus yk, and now this is less than or equal to summation ak square whole raised to half plus summation of bk square whole raised to half. K takes value 1 to n. This follows. Now, if you separate this, ak sigma ak square raised to half, and again sigma bk whole square raised to 1 by 2 power. So this is known as Minkowski inequality. By Minkowski inequality. The spelling is Minkowski. Inequality. So this inequality is in earlier chapter, that is infinite series. You can refer that, and it is direct. Summation ak plus bk whole square raised to half is less than or equal to summation ak square raised to half plus summation bk square raised to half. And but what is this? This is ak is we have xk minus zk, and therefore this will be summation k takes value 1 to n. ak is xk minus zk whole square raised to half plus bk is this value summation k takes value 1 to n zk minus yk square and again raised to half, and this is exactly row of x and z by definition. See, row of x and y is this. So instead of yk here it's zk. This is row of x and z plus row of this is z and y. And the starting is x, row of x and y, and there is the inequality less than or equal to. Thus, row of x and z is less than or equal to row of x and y. Row of x and y is less than or equal to row of x and z plus row of z and y. Hence, the triangle inequality is verified. See this. So you have used the definition, and here one inequality, Minkowski inequality, we have used, and thus this row is a metric. Hence, row is a metric for this Rn, space of n tuple, and this metric space is denoted by Rn itself and is called the Euclidean space. So this is our third example of metric space. So thus we have defined first a metric, which is a distance function having these four properties. And we have considered some examples of metric spaces set together with a metric defined on that set which satisfies these four properties. Then the function becomes metric and the space becomes metric space. So we have studied three examples, that is R1 with absolute value metric, then second is RD, that is a discrete metric space, and third we have just studied, that is Rn, that is Euclidean metric space. So these are three standard examples of metric spaces. Remaining examples we will continue in the next lecture. Thank you.